Hello, everyone. I think I'll go here, if it's OK. So this is joint work with Hang Le, and I want to mention that he's in the job market. So if this is relevant to any of you, I encourage you to contact him. So I'm going to talk about Euclidean spanners, which is a special type of spanners, where the graph is induced by a set of points in the plane or in the d-dimensional space. So let's consider a set S of n points in the plane. And you can see here at the bottom for illustrations. We're actually implicitly considering the complete weighted graph here, induced by the point set, where the vertices of this graph are the points and the weights are the Euclidean distances. And we say that H is a 1 plus epsilon spanner for the point set if, first of all, it's a spanning subgraph of G of S. And second, it approximates all the pairwise distances to within a factor of 1 plus epsilon. This means, in other words, that for any 2 points P and Q, there is a path in the spanner between them of total weight at most 1 plus epsilon times the Euclidean distance. And this parameter is called the stretch. So 1 plus epsilon is what we are looking for. And if you're considering this example, you can see that what we get here is 1 plus square root 2 stretch. And this is not what we are looking for. We would like to get very close to 1. We do not want to distort distances by too much. OK, so we are going mostly to talk about point sets in the plane. But the results will apply to higher dimensional spaces. OK, so the most basic parameter of spanners besides stretch is the size, the number of edges. And we can consider a normalized notion, sparsity, which is the ratio between the size of the spanner, the number of edges, and n minus 1, which is the minimum size of a connected graph. So ideally, we'll get a constant sparsity. And another basic parameter is the weight. The weight is the sum of all edge weights in the spanner. And here, too, we consider a normalized notion, lightness. The lightness is the ratio between the weight of the spanner and the weight of the minimum spanning tree. So here, again, we ideally want a constant bound. And there are other basic parameters. But we are going to focus on this, too. And we are trying to understand the precise trade-off between stretch, 1 plus epsilon, and the sparsity, or stretch 1 plus epsilon and the lightness. And the regime that we care about is very small epsilon, subconstant, some parameter, and constant dimensions. So why should we care about this? One reason is because Euclidean spanners find a bunch of applications. And in some of them, the focus is very low dimensional spaces, 2 and 3 in particular, and very small epsilon, because epsilon determines the precision. The smaller epsilon, the more precise we are. And the performance, because we are applying spanners here, the performance will depend in one way or the other on the sparsity and the lightness bound. So naturally, we would like to improve on them, if possible. OK, so what's known? A classic result from many years ago says that in any d-dimensional Euclidean space, there exists a 1 plus epsilon spanner with this sparsity, or in other words, n times epsilon to the 1 minus d edges. I'm omitting constants here. And it is achieved by various constructions. We don't know if this is optimal, even for 2-dimensional point sets. And so what we get for 2 dimensions is 1 over epsilon. Can we do square root of that? Maybe even more. And we'll see that it is impossible to improve on this classic bound, at least not in constant dimensions. The result for lightness is from the book of Narasimhan and Smith. And they showed that there is here just one candidate. The spanner here is the greedy spanner. And it was analyzed quite extensively. And it's been shown that for any point set in RD, there is a 1 plus epsilon spanner with this lightness, epsilon to the minus 2d. Here, there is some lower bound from a previous work with Elkin on a similar structure. It's called shallow light trees. And there we, at least for 2 dimensions, we got some lower bound. But you can see that there is still some big gap between the lower bound and the upper bound. So for dimension 2, the upper bound is epsilon to the minus 4. The lower bound is epsilon to the minus 1. Can we do better? And what about higher dimensions? So we'll see that the answer here is yes, we can do better. So let's see some more precise statements. So the sparsity bound is epsilon to the 1 minus d, and it's bound by several constructions. It turns out that there is a point set in RD for any constant d, for which any 1 plus epsilon spanner will have this lightness, so it's tight. You cannot do better than this classic bound. And surprisingly, there is a way to bypass this. I should mention that there should be quantifiers all over the place, and sometimes I omit them. If epsilon is very, very small, this will be huge. So we have to control epsilon, of course. And so it turns out that there is a way to bypass this hardness using Steiner points. Steiner points are points not in the input point set. They are additional points. And we show that they can lead to a quadratic improvement in the size. So essentially, whatever was known without Steiner points, we can get a square root of that with Steiner points. And this is going to be true whenever the dimension is constant. And every time you see a tilde here, I'm going to hide something. Okay, so there are many tildes. We are hiding usually very small, like polylogarithmic dependencies. And so for 2 dimensions, the upper bound is square root 1 over epsilon, and we show that it is tight. So this lower bound is for 2 dimensions. Okay, for lightness, what we show is that the greedy spanner can actually admit a better lightness. So by refining previous analysis, we can get a lightness of epsilon to the minus d, roughly, up to some tilde, some log factor. And we are not using any Steiner points here. It's just a more refined analysis of the same spanner. And we show that this is tight as well. So there are point sets for which any 1 plus epsilon spanner will incur this lightness. Okay, so to summarize, we get tight bounds for constant dimensional spaces. And we get quadratic improvement for both the size and the lightness. But for the size, we need Steiner points. And this is essential. There is actually a counterintuitive usage of Steiner points. I think many of you know that if you have a set of points in the plane and you want a minimum spanning tree, it's actually beneficial to use additional points that are not in your input. And this is the classic Steiner minimum tree problem. And you see that you can improve by adding this black point, you can improve the weight. But inherently, you are adding edges. And what we show is, in some sense, opposite. We show that you can actually reduce the number of edges using Steiner points. And we are not using Steiner points for reducing light or weight. Okay, so the last takeaway message is that the greedy spanner is optimal both in terms of size and lightness. And this refines a previous work with the filter, where we showed that essentially the greedy spanner is nearly optimal. Okay, so the starting point of this work starts with a very simple observation that I hope I'll be able to convey. And this observation is in the lower bound side. We just find the hard instance, and so let's see. In d dimensions, the hard instance will be the sphere, the d-dimensional sphere, but I want to focus mostly on the two-dimensional case. So here we are actually considering a unit circle, and we are plating roughly 1/epsilon points on the boundary of the circle. And then, in this way, the minimum distance between points along the circle is roughly epsilon. Let's say c times epsilon for a big enough c, constant c. And here is the observation. Any 1 plus epsilon spanner for this point set must include all the edges that connect points that are far away from each other, sufficiently far away from each other. But most pairs of points are far away from each other. So why is this true? The proof goes by contradiction. It's a very simple proof. I'll modulus some trigonometry, but we'll see. We are taking an arbitrary 1 plus epsilon spanner for this point set. And let's say that there are 2 points P and Q that are far away from each other. Let's say farther than square root 2, where the radius is 1. So they are far away, but there is no direct edge between them in the spanner. So how does the shortest path between P and Q look like? We know that it goes through at least one intermediate point. Let's denote it by x. So by the triangle inequality, the distance between P and Q in the spanner is at least the Euclidean distance between P and x plus the Euclidean distance between x and q. But we also know that all these points lie on the circle, on the boundary of the circle. And we also know that P and Q are very far from each other. And one last property that we use is that x is far, quite far, not too far, quite far from both P and Q, at least c times epsilon apart. And this is all we need. So this is just simple trigonometry that shows that the distance must be bigger than 1 plus epsilon times the Euclidean distance between P and Q. And this means that this is not a 1 plus epsilon spanner. So in other words, the corollary is that for this particular point set, you have to use many edges, and all of them have large weight. And when I say large weight, I mean weight that is linear in the weight of the minimum spanning tree. Because for this point set, the minimum spanning tree is just, you connect them by a simple path. So it's just the perimeter of the circle minus some epsilon. So every one of those edges that we know are in the spanner have weight linear in the weight of the MST. And this means that we have this many edges, quadratic in the number of points, and this lightness, epsilon to the minus 2. OK, so this concludes the lightness bound. To be more precise, we actually need to throw some more points so that there are n points overall. But we just throw all of them to coincide with one arbitrary point that is already in the points that you see. And this doesn't change the weight of the MST. And it also doesn't change the argument. So the lightness is fine. In terms of the sparsity, we have to be a bit more careful, because you cannot just throw more points. It reduces the sparsity. So in order to scale correctly, we need to create multiple copies of the same point set and to space them apart in an appropriate distance from each other. And then it's not difficult to verify that the lower bound will scale smoothly and will get the desired sparsity bound. Okay, so this is the idea for the lower bound in 2 dimensions. In d dimensions, we use this simple observation. Some tweaks make it work in d dimensions, but we also combine it with known packing arguments, classic arguments. They are known maybe as spherical codes. And what we know is that you can pack many vectors to the unit sphere so that the minimum distance between any 2 vectors will be at least epsilon. And the number of vectors that you can pack is this. And I'm ignoring dependencies. So let's assume that the dimension is constant here. If not, we need to throw some exponential in D. But by using this packing property with a simple observation from before, we get the lower bound for any dimensions. And then this lower bound for sparsity matches the upper bound that we mentioned, the classic upper bound, order epsilon to the 1 minus d. But for the lightness, we are still pretty far, because this only shows epsilon to the minus d, and the upper bound that was known was epsilon to the minus 2d. And so we need to go from this to that, and it's a pretty technically long and tedious argument. I will not give any details about that. But we are not done in terms of lightness. We have to work hard for the upper bound. And now I have just, 4 minutes or so. So yeah, okay, so as far as I'm concerned, this is the highlight of the work, because we are using Steiner points to improve classic sparsity bound in an unexpected way. And so I had to choose whether I focus on the lower bound or the upper bound. And I chose the upper bound because it's more accessible, I think. Let me just say that lower bounds for Steiner spanners are pretty elusive. And the intuition is that it's tricky to reason about points that are not in your input. So I think this is what I want to say about lower bounds for Steiner spanners. This is probably the most technically challenging part of the paper. I want to talk about the upper bound because it's more accessible, and I'm going to focus on 2 dimensions, but whatever I'm saying is generalized quite smoothly to any constant dimension. So the strategy will be pretty natural, I think. First, we have this warm-up observation. Let's start with that. So we mentioned that if we place on the boundary of the circle points evenly, then we get a hard instance. The same hard instance we will get if we place them on the square. It doesn't really matter, but it's more, it's instructive to use the square for this argument. So now let's just look at the upper side and the lower sides. We have 1 over epsilon points here, 1 over epsilon points there, and by the same argument that I said before, if the constants are calibrated correctly, any 1 plus epsilon spanner for this point set should contain this complete bipartite graph. So it should contain all those edges. Because if any one of them is missing, then the stretch will be violated, the stretch of 1 plus epsilon. OK, so we have this. This is a graph with the sparsity 1 over epsilon. The number of edges is quadratic in the number of points. The number of points is 1 over epsilon, so it's sparsity 1 over epsilon. We want to improve this using Steiner points. So what we are doing is very natural. We just take this straight line horizontally in the middle, and we place fewer Steiner points, much fewer, like square root of the original points. The number of original points is 1 over epsilon. We are going to spread here square root of that. So the distance between Steiner points is longer, but that is still fine. What we are doing, we are replacing this dense structure by a sparser structure. We just connect every Steiner point to every original point, so that original points are not connected directly. They have to go through Steiner points. And it's not difficult. It's like a simple exercise to see that this is a 1 plus epsilon spanner. But the number of edges is reduced. The sparsity now is going to be square root 1 over epsilon. And yeah, so now this square is not so special. We can actually distort things up a bit. So for example, instead of the points on the upper side of the square, we can place them in some rectangle here and rectangle here. And if the rectangles are far enough, we can place Steiner points in the middle and do the same trick again, and we'll get the same sparsity improvement. So this is the first part of the strategy. The second part is to employ this recursively. Okay, so there are some details here, of course, but we take a big enough square. Yeah, I'm finishing in less than a minute. So we take a big enough square of side length delta that encloses all the points. And all the pairwise distances that are large are handled by the warm-up observation from before. It's very easy to connect all the points that are far from each other using the warm-up observation and very few edges. Actually, the crux is the short distances, the small distances. And we handle them recursively. So we break this square into subsquares, and we proceed recursively. The only catch is with neighboring, like points that belong to neighboring squares. There could be very short distances here, very small distances here. So we just make sure that we increase the sizes of the subsquares a bit so that they overlap. And with this overlapping, we can also handle such pairwise distances. And you do the analysis, and you see that the total number of edges the sparsity is 1 over square root epsilon. And there is some annoying term that depends on the size length of the square, or more generally, the aspect ratio, for those who are familiar with this term. And then the aspect ratio could be huge. And so the last step is to reduce the general case to the case where the aspect ratio is bounded by, let's say, 1 over epsilon. And we do this by borrowing ideas and constructions from a wider family of doubling metrics, like the netric spanner. And I think I'll stop here. So thanks.
Questions? Okay, I guess not. Okay, let's thank Shay again.